Balancing equations by oxidation reduction. In this equation, copper oxide and ammonia react to form copper and nitrogen. We can see two problems. First, there is one oxygen atom here on the left, but no oxygen atoms on the right. There's hydrogen here on the left, and again no hydrogen on the right. This lesson will show you how to deal with this situation, as well as equations that contain ions with charges on them. This wasn't possible with the earlier method of inspection. We're going to use a method called the oxidation number method, or half-cell method. This will be useful later on in another unit of electrochemistry. First, we'll assign oxidation numbers to those elements undergoing a change in their oxidation states. For example, this is copper 2+. Copper in its elemental state is 0. It's assumed that you have previously learned how to assign oxidation numbers to atoms. Since the oxidation number has been reduced from 2+ to 0, we call this a reduction. Now nitrogen is 3- here, and by the way, just to pause, it's unusual to see an element with a negative valence as the first element in a formula. Normally the first element has a positive valence, but the history of writing ammonia like this is so long that it's not likely to change, but it's something we can easily live with, and it's the only common compound like this. Over here, nitrogen is 0 because it's in its elemental state, and so we have the oxidation number going up from 3- to 0, which we call oxidation. Now we write the oxidation and reduction equations. Ammonia going to nitrogen, and copper oxide going to copper. Now we'll balance the elements undergoing reduction and oxidation. The word redox here refers to reduction and oxidation. It is commonly used as a short form. This too will balance the nitrogens. Copper is already balanced in the reduction. We must always make sure that half reactions are balanced for the elements that change oxidation states before proceeding. Now we balance for electrons. This is done by comparing the total oxidation numbers. The total oxidation number for these two nitrogen atoms is 6-. That is 3- times 2. The total oxidation number for N2 is still 0, so 6 electrons were given off, which we show as a product. By definition, oxidation is the loss of electrons, so each nitrogen atom here has lost 3 electrons to become 0. This half reaction is now balanced for charge, 6- on the left and 6- the electrons on the right. In the reduction of copper oxide, we're going from a 2+ down to 0. So in this case, the copper must have gained 2 electrons. Recall that by definition, in a reduction, an atom gains electrons, and the copper here has gained 2 electrons. Now we multiply each equation by a suitable number so that the electrons cancel out when the equations are added up. Electrons never appear in a final equation. Then add the equations and bring down any compounds that were not used from the original equation. This part isn't needed for this example, but it will come up in the last practice problem. So we multiply the reduction by 3, which gives 6 electrons in each half reaction, and they will cancel out or add up to 0. Here it is. The main elements, copper and nitrogen, are balanced, but not oxygen or hydrogen. Now notice there are 3 oxygen atoms on the left and none on the right. The solution is to add water to balance oxygen. So we add 3 H2Os now. Now you see that we have also introduced 6 hydrogen atoms from the water, and you notice here we have 6 hydrogen atoms in ammonia. adding H plus is not needed in this example. If it is needed, always make sure to add water and hydrogen ions in this order. First the water and then the hydrogen ion. This equation is now balanced. By the way, the addition of water and hydrogen ion may seem like we're fudging it, but remember, most reactions take place in aqueous solution where there is plenty of water, so that is available, and water always contains hydrogen ions as well as hydroxide ions, usually more of one than the other, to give us either acidic or basic solution. So these ions are always available for us to balance a reaction. We'll now look at one more example which shows how to deal with charged ions and with the instruction to balance in basic medium or solution. In this example, the dichromate ion reacts with chloride ion to produce chromium 3+ ion and chlorine. We're asked to balance it in a basic medium. The first thing to do is to determine the oxidation states of those elements undergoing a change as we did in the previous example. What is the oxidation state of chromium? We always start with the element we know, which here will be oxygen. In most cases, oxygen is 2-. So 7 oxygens times 2- gives a total oxidation number of 14-. Now, these two chromiums have to add up to a number which, when added to 14- gives you a net charge of -2. That's going to be 12+. So an individual single chromium will be 12 divided by 2, which is 6+, the oxidation state for a single chromium atom. Since each chromium is 6+, the oxidation number has been reduced from 6+ to 3+, making this a reduction. The chlorine has gone up from 1- to 0, thus making it the oxidation. Let's write the oxidation and reduction reactions. First, balance each half reaction with a 2 here for chlorine and a 2 here for chromium. The total oxidation number for these two chloride ions is 2-, and for Cl2, 0. Oxidation is loss of electrons, so 2 electrons show here as products. The total oxidation number for chromium is 12+, as we see from above. The total oxidation number for Cr3+ is 6+. So in this reduction reaction, 6 electrons were gained in order to get from 12+ down to a 6+. We need to have the same number of electrons in each half reaction, so we multiply the oxidation by 3 to give us 6 electrons. Adding them up gives 1 dichromate plus 6 chloride ions to produce 3 chlorine molecules plus 2 chromium 3+ ions. The main elements, chromium and chlorine, are balanced, but not oxygen. We'll add 7 molecules of water to balance the oxygens. This introduces 14 hydrogens, but there are no hydrogens on the left. This is solved by adding 14 H+ ions on the left. This equation is now balanced in acidic medium as shown by the presence of the hydrogen ions. Now, to balance in a basic solution, we will add the correct number of hydroxide ions to neutralize the 14 hydrogen ions, and then add the same number of hydroxide ions to the opposite side. Since H+ and OH- can combine to form water, we combine these ions and form 14 molecules of water. The ions disappear, and we have 14 water molecules on the left side. We have 7 on the right, so adding them up algebraically will leave us with 7 H2O on the left. And now this equation is finally balanced. The presence of the hydroxide ions here tells us that this equation is balanced in a basic medium. It's not only mass balanced, it is also charge balanced, and we should check this out. Let's add up the total charge on the left side and see if it balances the right. Here we have 2 minus, and here we have 6 minus. So that's a total charge of 8 minus on the left. The 2 chromiums give 6 plus, the 14 hydroxides give 14 minus. 14 minus and 6 plus add up to 8 minus, which equals the charge on the left side. So that is what is meant by saying that an equation is charge balanced and mass balanced, and this must always be true for any balanced equation. This is likely the most complicated type of question that you're going to get at the high school level. A final type of equation for balancing is called disproportionation. A short video on this is available from the link below. All that remains now is for you to do some practice problems. There are 6 of them. Before you start, I'll explain that I will first give the answer, and then if you didn't get it, show the basic redox reactions, except for number 6, which I will do in detail. You could stop now and try the ones that you would like to, and then come back and see how you did. Here's the first one. And here are the redox reactions. Here's the second one, and the redox reactions. Here's the third one. Now, this is what you would first get before you do the final step for basic solution. And here is the final balanced equation. Here are the redox reactions. Here's the answer to number 4. The redox reactions. Number 5, the first step before you do the final basic step. Here's the balanced final reaction and the redox reactions. And here is the answer for number 6. I will do this one in detail now, as it shows how to deal with a compound that does not undergo redox. The first thing to determine is which elements are going oxidation and reduction. For nitrogen, first see that 3 oxygens give an oxidation number of 6 minus. So nitrogen must be 5 plus so that we get the -1 charge on nitrate. This nitrogen is 2 plus to balance the 2 minus of oxygen. Sulfur as an element is 0. Sulfur in arsenic sulfide is its normal 2 minus. Here is the oxidation reaction. Remember that we must first balance the element undergoing the change. So we need 5 here to balance the sulfur. The total oxidation number for the 5 sulfurs is 10 minus. Going from 10 minus to 0 means 10 electrons were given off or lost. For the reduction, nitrogen goes from 5 plus to 2 plus. So there must have been a gain of 3 electrons in this reduction. Since the number of electrons must be the same in each half reaction, we multiply by 3 here and 10 here to get 30 electrons for each reaction. Adding gives this so far. Now look at arsenic acid. No atoms in the arsenic acid have undergone an oxidation or reduction. In this situation, we simply bring it down to be part of the final equation. To balance the 6 arsenics on the left, we put a 6 here. Continue adding gives us 15 sulfurs and 10 NO. Balance oxygen first. We have 34 on the right and 30 oxygens on the left. So we must add 4 waters, and that balances oxygen. Now for hydrogen. There are 8 on the left and 18 on the right. So we must add 10 H pluses. The equation is now balanced in acidic medium. This ends the video on balancing redox reactions.